Hello. This is yet another simple problem from the chapter First Law of Thermodynamics for Open System. It is given that the steam flows through a turbine with a flow rate of 5,000 kilograms per hour. So we can note down that the system is an open system as turbine is a flow device. Also, we shall assume the flow to be a steady flow, as it is not explicitly given in the problem. And the substance or fluid used in the turbine is steam. M dot is equal to 5,000 kilograms per hour, which is equal to 1.389 kilograms per second. We know that in the steam turbine, the expansion process takes place, due to which work is produced. So this turbine is developing a power of 550 kilowatt. So we can write W.12 is 550 kilowatt. And the heat loss from the turbine casing and in the bearing is considered to be negligible. So Q.12 will be 0. And we can also say that the expansion process 1-2 is the adiabatic process. Of course, in the first law, we assume the processes to be reversible, which will make this process as reversible adiabatic or isentropic process. Now, since the fluid is steam, which could be wet, consisting of water particles, we can't assume the process index relation is shown. And for this data, we have to find the change in enthalpy for two cases. In the first case, we have to consider the inlet velocity v bar 1 equal to 0. The exit velocity v bar 2 equal to 360 meter per second. Whereas the change in potential energy is considered to be negligible or 0. So we can write delta PE is equal to 0. Which means that Z1 is equal to Z2. Whereas, in the second case, we again have to find the same change in enthalpy for process 1-2, for the same exit velocity of 360 meter per second. But in this case, the inlet velocity is considered, and it's taken as 66 meter per second. Whereas, the inlet pipe is at 3 meter elevation, above the exit pipe. So we can write Z1 is equal to Z2 plus 3. Or Z2 minus Z1 is equal to minus 3. Alright? We may also note that we will determine the total change in enthalpy, as mass flow rate term is given. This m dot data makes the calculation of total quantities possible. Right. So let's start with the solution. We first draw a schematic figure of a steam turbine, where the fluid, which is steam, is flowing from inlet 1 to outlet 2. With the following values of mass flow rate and energy transfer. Now, let us first consider the case 1, where the inlet and outlet condition data is as shown. So, we first start with delta H12 for case 1. We know we get the enthalpy values for the open system processes from the steady flow energy equation. So, using the steady flow energy equation for expansion process 1-2, we can write Q.12 minus W.12 is equal to m dot into delta PE plus delta KE plus delta H of 1-2. So, now elaborating the formulas for delta PE, delta KE, and delta H, we can write Q.12 minus W.12 is equal to m dot into G into Z2 minus Z1 upon 1000 plus V bar 2 square minus V bar 1 square upon 2000 plus delta H of 1-2. Alright. Now we see that we have the values of Q.12, W.12, m dot, and both velocity and Z values. Since Z1 is same as that of Z2, the delta PE term will be 0. So, simply substituting the values, we can write 0 minus 550 is equal to 1.389 into 0 plus 360 square minus 0 upon 2000 plus delta H of 1-2. So, after calculation, we get delta H of 1-2 is equal to minus 460.77 kilojoules per kg. Now, this is a specific change in enthalpy. To get the total change in enthalpy, we simply multiply it with the mass flow rate term m dot. So we get the total change in enthalpy, delta H12 equal to 1.389 into minus 460.77. So the answer we get is minus 640 kilowatt. This is our first answer for case 1. Now, let's go to case 2, where the turbine inlet and outlet conditions are as shown. In this case, both the inlet velocity and change in potential energy is taken into consideration. Now, we will simply repeat the same procedure to find out the change in enthalpy. In this case also, we get the following expressions. Now again substituting all the required data in the above steady flow energy equation, we can write 0 minus 550 is equal to 1.389 into 9.81 into minus 3 upon 1000 plus 360 square minus 66 square upon 2000 plus delta H of 12. So on calculation, we get the change in specific enthalpy, delta H12 is equal to minus 458.56 kJ per kg. And the total change in enthalpy in process 1-2, in case 2 is equal to 1.389 into minus 458.56. So we get the answer as minus 636.94 kilowatt. And this is our second answer. So if we compare both the answers, we see that there is a very small difference in the value of change in enthalpy. So neglecting the initial velocity v bar 1, as well as the change in the potential energy, does not compromise the accuracy of calculation to a significant extent, right? So this is the reason why in most of the cases, we neglect the inlet velocity of the turbine, as well as the change in the potential energy. So this problem was actually a small exercise to analyze the same. Clear? We may also see that the change in enthalpy is negative, which again confirms that the turbine is a device which produces positive power at the expense of enthalpy, meaning that the enthalpy of fluid or steam decreases during expansion.